Welcome to your CCNA complete course. Whether you're diving into networking for the first time or polishing your skills for that career-changing certification, this is your ultimate guide to mastering everything, from basic network concepts to the 7-layer OSI model. We're going to cover 20% of your entire CCNA 200-301 exam in just 1 hour. But don't worry. We'll keep it engaging, clear, and surprisingly easy to understand. Think of it like building a networking foundation. We'll start with the basics and stack each concept perfectly so you're ready to tackle any networking challenge. So grab your favorite study snack, get comfortable, and let's make sure you're ready to ace this exam. Like this video if you're tired of confusing networking explanations, and subscribe for clear, practical CCNA content. This crash course is designed as a concise, high-speed overview, providing you with streamlined explanations of critical CCNA objectives. Think of it as your roadmap. Instead of memorizing everything line by line, prioritize the bigger concepts and the logic behind each topic. Make use of the included memory hacks, mnemonics, or quick reference guides to quickly retrieve the essential facts on test day. As you go through each slide, try to apply new knowledge immediately, whether by running commands in Packet Tracer or configuring settings on practice equipment. If you find a topic overly familiar, feel free to move on and revisit it only if needed. This flexible method ensures you focus on the concepts that will truly boost your exam performance and real-world networking skills. Networks are at the heart of modern computing, facilitating resource sharing, communication, and data exchange between devices. Home networks, enterprise networks, and the Internet all share the core function of connecting devices to enable collaboration and information access. They provide pathways for data transmission, whether through cables, wireless signals, or fiber optic connections, and enforce protocols that ensure reliable communication. A well-designed network is critical to business operations and personal productivity, managing traffic flow and maintaining security boundaries. By imagining a network as a highway system connecting different cities, you can better appreciate why proper planning, protocols, and maintenance are so vital. Grasping foundational network principles supports more effective troubleshooting, performance optimization, and security implementation. A computer network is simply two or more devices connected together to share resources, communicate, and exchange data. These devices can include computers, smartphones, printers, servers, and routers working together as an interconnected system. Networks enable resource sharing like printers and internet connections, facilitate communication through email and messaging, provide centralized data storage and backup, and allow for centralized management of devices and security. The beauty of networking lies in its transparency to end users. Your laptop doesn't care if it's connected via Wi-Fi, Ethernet, or through multiple intermediary devices. A handy way to remember network benefits is RCSM, Resource Sharing, Communication, Storage, Management, which covers the 4 primary reasons we create networks in the first place. Every network consists of 3 fundamental component types, and understanding these is crucial for the CCNA exam because Cisco organizes everything around this model. End devices, also called hosts, are the devices that actually use the network. Computers, smartphones, printers, servers, and tablets that host applications and services. Intermediary devices connect the end devices and direct data through the network, including switches for local connections, routers for connecting different networks, access points for wireless connectivity, and firewalls for security. Network media carries the actual data, including copper cables like Ethernet for local connections, fiber optic cables for high-speed, long-distance transmission, and wireless signals for mobility and convenience. These 3 components work together seamlessly, with the network remaining transparent to end users who simply see connectivity, regardless of the underlying infrastructure complexity. Network architectures define how devices interact and share resources, with two primary models dominating modern networking. Client-server architecture features centralized servers providing services to multiple clients that request those services, like web servers serving pages to browsers, email servers managing messages, or file servers storing shared documents. This model offers centralized administration and security, better performance and reliability, easier backup and maintenance, and excellent scalability for larger networks. Peer-to-peer (P2P) architecture allows every device to act as both client and server, sharing resources directly. This is common in small office networks for printer sharing or in applications like BitTorrent file sharing. For your CCNA exam, remember that enterprise networks heavily favor client-server architecture due to centralized control and security benefits, making it the focus of most Cisco scenarios and configurations. Networks are categorized by their geographical scope and ownership, with each type having distinct characteristics important for the CCNA exam. Personal area networks, PANs, cover your personal space up to 10 meters, connecting devices like smartphones to Bluetooth earbuds, laptops to wireless mice, or tablets to styluses using technologies like Bluetooth, USB, and NFC. Local area networks, LANs, connect devices in a single location like homes or offices, featuring single organizational ownership. High speeds from 100 megabytes to 10 gigabytes, low latency for fast response times, and limited geographical coverage using Ethernet and Wi-Fi technologies. Wide area networks, WANs, connect networks across large geographical distances using multiple service providers, typically offering lower speeds than LANs, but improving with fiber technology. Higher latency due to distance and higher costs, with the Internet being the ultimate example of a WAN connecting networks globally. Network topologies describe how devices are physically connected and how data logically flows through the network. Understanding the distinction between physical and logical topologies is crucial. Physical topology shows actual cable connections you can touch, while logical topology shows the path data takes, which can be completely different. Star topology connects all devices to a central point like a switch, offering easy installation and management. Isolated cable failures affecting only single devices. Easy expansion, but creating a single point of failure if the central device fails. Bus topology connects all devices to a single backbone cable, using less cable but creating network-wide failures if the backbone breaks. Ring topology connects devices in a circular chain with predictable performance but difficult troubleshooting. Mesh topology provides multiple paths between devices for maximum reliability but at a higher cost and complexity. For the CCNA exam, focus heavily on star topology as it dominates modern networks and Cisco lab scenarios. The Open Systems Interconnection, OSI model, is the most important concept in all of networking, breaking down the complex process of network communication into 7 manageable layers. This conceptual framework provides standardization by creating a common language for network professionals, enables effective troubleshooting by isolating problems to specific layers, supports systematic design by addressing each layer independently, and facilitates education by making complex networking understandable. The model works by having data travel down the layers, 7 to 1, on the sending device across the network, then up the layers, 1 to 7, on the receiving device. Each layer adds its own header during encapsulation, creating a structured approach to a network communication. The famous mnemonic, "Please do not throw sausage pizza away," helps us remember the layers: physical, data link, network, transport, session, presentation, and application. The physical layer handles the actual transmission of raw bits over physical media, converting data into electrical signals, light pulses, or radio waves. Key functions include defining cable specifications and connector types, specifying voltage levels and signal timing, managing the physical transmission methods, and handling the conversion between digital data and physical signals. Physical media includes copper cables like UTP, unshielded twisted pair, for local connections that are inexpensive and easy to install, but limited in distance and susceptible to interference. Fiber optic cables provide high-speed, long-distance transmission, immunity to electromagnetic interference, and excellent security, but cost more and require specialized equipment. Wireless transmission offers mobility and easy deployment, but faces security concerns, interference issues, and distance limitations. Common Layer 1 problems include cable faults, connector issues, interference, distance limitations, and power problems. Remember, if you can physically touch it, it's likely a Layer 1 component. The data link layer ensures reliable communication between directly connected devices using physical addresses called MAC addresses. This layer handles framing by organizing bits into structured frames. Physical addressing using 48-bit MAC addresses for local delivery. Error detection through frame check sequences, and flow control to manage transmission rates. Ethernet frames contain a preamble for synchronization, start frame delimiter, destination and source MAC addresses, length type field, data payload, and frame check sequence for error detection. MAC addresses consist of 48 bits, 6 bytes with the first 24 bits identifying the manufacturer, OUI, and the last 24 bits uniquely identifying the device. Switches operate at Layer 2 by learning MAC addresses, flooding unknown destinations to all ports, forwarding known destinations to specific ports, and filtering traffic within collision domains. Understanding Layer 2 is crucial because it handles local delivery, getting frames from one device to the next hop using MAC addresses that only work on the local network segment. The network layer provides logical addressing and routing, enabling end-to-end communication across multiple networks using IP addresses. Key functions include logical addressing with IPv4, 32-bit, and IPv6, 128-bit addresses, path determination through routing table consultations, packet forwarding between different networks, and fragmentation when packets exceed link capacity. IP addresses consist of a network portion, identifying the specific network, and a host portion, identifying devices within that network. Routing works through a 4-step process: examining destination IP addresses, consulting routing tables for best paths, forwarding packets to next hop routers, and repeating until packets reach final destinations. Important Layer 3 protocols include IP for primary addressing and routing, ICMP for error messages and diagnostics like ping, ARP or ARP for mapping IP addresses to MAC addresses, and routing protocols like OSPF and EIGRP. The crucial distinction between layers is that Layer 2 MAC addresses change at every hop for local delivery, while Layer 3 IP addresses remain constant from source to destination, providing end-to-end addressing. The transport layer provides reliable end-to-end data delivery and manages communication between applications through port numbers. This layer handles segmentation by breaking large data into manageable pieces, reliability through connection establishment and error recovery, flow control by managing transmission speeds, and application identification using port numbers. TCP, Transmission Control Protocol, is connection-oriented and reliable, guaranteeing data delivery and maintaining proper order through a 3-way handshake. Synchronize, acknowledge, but operates slower due to overhead. UDP, User Datagram Protocol, is connectionless and fast with no delivery guarantees, making it perfect for applications where speed matters more than perfect delivery. Use TCP for web browsing, HTTP, HTTPS, email, SMTP, file transfers, FTP, and any application requiring reliable delivery. Use UDP for DNS queries requiring fast lookups, video streaming where some loss is acceptable, online gaming needing real-time response, and DHCP for simple request-response communication. Memorize these common port numbers for the CCNA exam: HTTP 80, HTTPS 443, SSH 22, Telnet 23, FTP 20 and 21, DNS 53, DHCP 6768. The upper three layers of the OSI model work closely together with many protocols operating across multiple layers. Layer 5, Session Layer, establishes, manages, and terminates communication sessions between applications, handling dialog control for half-duplex or full-duplex communication, and providing session checkpointing for recovery. Layer 6, Presentation Layer, manages data formatting and conversion, encryption and decryption for security, compression and decompression for efficiency, and character encoding like ASIC or Unicode. Layer 7, Application Layer, provides network services directly to end users and applications, including web browsers using HTTP, HTTPS, email clients using SMTP, POP3, IMAP, file transfer using FTP, and domain name resolution using DNS. These layers work together seamlessly. When you browse the web, the application layer creates HTTP requests. The presentation layer may add SSL encryption. The session layer manages the connection. And everything flows down through the lower layers for actual transmission across the network. While the OSI model provides excellent conceptual understanding, the TCP/IP model represents what's actually implemented in real networks today. This four-layer model combines OSI functionality. The application layer merges OSI layers 5, 6, and 7 into network services. The transport layer matches OSI layer 4 with TCP and UDP. The internet layer corresponds to OSI layer 3 with IP addressing and routing, and the network access layer combines OSI layers 1 and 2 for physical transmission and local delivery. TCP/IP became the standard because it was developed alongside the internet, proven to work in real networks, more flexible and less rigid than the pure OSI approach, and widely adopted across all networking equipment. The Internet Protocol Suite includes application layer protocols like HTTP, FTP, SMTP, and DNS. Transport layer protocols, TCP and UDP. Internet layer protocols, IPv4, IPv6, ICMP, and ARP. And network access layer technologies like Ethernet and Wi-Fi. Understanding how data travels through network layers is crucial for troubleshooting and network design. The encapsulation process begins when applications create raw data to be transmitted across the network. At the transport layer, data becomes segments, TCP or datagrams, UDP, with added headers containing source and destination port numbers, sequence numbers for TCP, and control flags for connection management. The network layer creates packets by adding IP headers with source and destination IP addresses, time to live (TTL) values, and protocol identification. The data link layer forms frames by adding Ethernet headers with source and destination MAC addresses, and trailers with frame check sequences for error detection. Finally, the physical layer converts frames into bits transmitted as electrical signals, light pulses, or radio waves over the chosen medium. The receiving device reverses this process through de-encapsulation, removing headers at each layer until original application data is recovered and delivered to the destination application. Each OSI layer uses specific names for its data units, called Protocol Data Units, PDUs, which is important terminology for the CCNA exam. Layers 7 through 5, application, presentation, session, work with raw data containing no network headers yet. Layer 4, transport, creates segments for TCP or datagrams for UDP by adding transport headers with port numbers identifying applications. Layer 3, network, forms packets by adding IP headers with source and destination addresses, providing end-to-end addressing. Layer 2, data link, constructs frames by adding frame headers and trailers with MAC addresses for hop-to-hop delivery. Layer 1, physical, transmits everything as bits converted to electrical, optical, or radio signals. A helpful memory aid: do some people forget birthdays? For data, segments, packets, frames, bits. Understanding PDUs is crucial for troubleshooting. When someone says we're dropping packets, they're referring to Layer 3 problems, while corrupted frames indicate Layer 2 issues. Let's trace exactly what happens when you visit a website, demonstrating all OSI layers working together. First, DNS resolution occurs when your computer queries DNS servers to convert www.example.com into an IP address, involving application layer DNS protocols, transport layer UDP on port 53, network layer IP addressing to reach DNS servers, data link layer Ethernet frames on your LAN, and physical layer electrical signals over cables. Next, your browser creates an HTTP request with the application layer generating the HTTP GET request. Presentation layer potentially adding SSL encryption for HTTPS. Session layer establishing the connection. Transport layer using TCP on port 80 or 443. Network layer creating IP packets with destination server address. Data link layer adding Ethernet frames with router MAC address. And physical layer transmitting signals over your network connection. The request then travels across multiple networks, with routers examining Layer 3 destination IPs, creating new Layer 2 frames for each hop, while Layer 1 carries signals over various physical media. Finally, the web server processes your request and responds, with the same encapsulation process delivering the web page back to your browser through all 7 layers. The OSI model provides a systematic approach to network troubleshooting, allowing you to isolate problems to specific layers. Use either a bottom-up approach starting at Layer 1 and working upward, or a top-down approach beginning at Layer 7 and working downward. Layer 1 physical problems show complete connectivity loss with symptoms like unplugged cables, broken wires, or power failures. Use cable testers, visual inspection, and link lights for diagnosis. Layer 2 data link issues cause local connectivity problems with high error rates, often from switch failures, VLAN misconfigurations, or duplex mismatches. Check the switch's MAC address tables and interface statistics. Layer 3 network problems prevent reaching remote networks with symptoms like wrong IP addresses, missing routes, or router failures. Use ping, traceroute, and routing table analysis. Layer 4 transport issues cause application timeouts and connection failures from firewall port blocking or TCP window problems. Test with Telnet to specific ports. Layer 7 application problems affect specific services like web servers being down or DNS failures. Use application-specific tools and service logs. This systematic approach quickly isolates problem layers, saving time and preventing random troubleshooting attempts. Understanding complete network communication flow reinforces OSI model concepts and prepares you for real-world scenarios. When you send an email, the application layer creates SMT commands and message content. The presentation layer may encrypt the content and format text. The session layer establishes a session with the mail server. The transport layer uses TCP on port 25 to ensure reliable delivery. The network layer adds IP headers with mail server addresses. The data link layer creates Ethernet frames for local delivery to your router. And the physical layer converts everything to electrical signals. Your email then travels through your ISP's network, across internet backbone networks and to the destination's mail servers network, with each router making Layer 3 routing decisions and creating new Layer 2 frames for each network segment. At the destination, the process reverses as the mail server receives the physical signals, processes frames, examines packets, handles TCP segments, manages the SMTP session, and finally delivers your mail to the recipient's mailbox through all 7 layers working in perfect coordination. Network protocols operate at different OSI layers, and understanding their placement is crucial for CCNA success. Application layer protocols include HTTP, HTTPS for web traffic on ports 80 and 443 respectively, FTP for file transfers on ports 20 and 21, SMTP for sending email on port 25, DNS for name resolution on port 53, DHCP for automatic IP configuration on ports 67 and 68, and Telnet SSH for remote access on ports 23 and 22 respectively. Transport layer protocols features TCP for reliable connection-oriented communication and UDP for fast connectionless transmission. Network layer protocols encompass IPv4 and IPv6 for addressing and routing, ICMP for error messages and ping functionality, and ARP for mapping IP addresses to MAC addresses. Data link layer protocols include Ethernet for wired LANs, Wi-Fi 802.11 for wireless networks, and PPP for point-to-point connections. Understanding protocol placement helps with troubleshooting. If DNS isn't working, you know it's an application layer issue, while ping failures indicate network layer problems. Real-world networking scenarios demonstrate how OSI layers interact in everyday situations. When your Wi-Fi connection drops, potential issues span multiple layers. Physical layer problems like interface from microwave ovens or distance from access points. Data link layer issues with wireless security or SSID configuration. Network layer problems with IP address conflicts or DHCP failures. And application layer issues with specific services failing while others work. For slow internet browsing, investigate physical layer bandwidth limitations or cable problems. Data link layer switch performance or VLAN configurations. Network layer routing inefficiencies or congestion. Transport layer TCP window sizing, and application layer web server performance. When printers aren't working on the network, check physical layer cable connections, data link layer switch port configurations, network layer IP address assignments, transport layer print service ports, and application layer printer driver installations. This layered approach ensures comprehensive problem solving and prevents overlooking critical issues. Network security operates across all OSI layers, with each layer contributing to overall protection. Physical layer security includes locked server rooms, cable protection, and secure access to network equipment. Data link layer security features switch port security, MAC address filtering, and VLAN segmentation to control local network access. Network layer security implements access control lists, ACLs, firewalls for packet filtering, and VPNs for secure communication across untrusted networks. Transport layer security utilizes SSL TLS encryption for application data protection and port-based filtering for service access control. Application layer security encompasses user authentication, application-specific security measures, and secure protocols like HTTPS instead of HTTP. Understanding security at each layer helps implement defense-in-depth strategies, where multiple security measures work together to protect network assets. For the CCNA exam, focus on access control lists, ACLs, for packet filtering, VLANs for network segmentation, and basic firewall concepts for perimeter defense. Network performance optimization requires understanding bottlenecks at different OSI layers. Physical layer optimization includes upgrading from copper to fiber for higher bandwidth, using proper cable categories, Cat6 versus Cat5e, and minimizing electromagnetic interference sources. Data link layer improvements involve upgrading switch hardware for better forwarding rates, implementing VLANs to reduce broadcast domains, and configuring proper duplex settings to avoid collisions. Network layer optimization features efficient routing protocol configurations, proper IP addressing schemes to minimize routing table size, and quality of service (QoS) implementations for traffic prioritization. Transport layer enhancements include TCP window sizing for optimal throughput, proper port configurations for applications, and load balancing across multiple connections. Application layer optimizations encompass caching mechanisms, content delivery networks (CDNs), and application-specific tuning. Understanding performance at each layer enables targeted improvements rather than generic, faster internet solutions. The transition from IPv4 to IPv6 represents a significant network layer evolution driven by address exhaustion and enhanced features. IPv4 uses 32-bit addresses, providing approximately 4.3 billion addresses, which seemed unlimited initially but proved insufficient for global internet growth. IPv6 employs 128-bit addressing, offering virtually unlimited addressing space. Built-in security features with IPsec, simplified header format for improved processing efficiency, and automatic address configuration capabilities. Transition mechanisms include dual stack configurations running both IPv4 and IPv6 simultaneously, tunneling IPv6 traffic over IPv4 infrastructure, and translation services converting between address formats. For the CCNA exam, understand basic IPv6 address structure with network prefixes, typically /64, interface identifiers derived from MAC addresses, and special addresses like link local, FE80::/10, and unique local, FC00::/7. IPv6 adoption continues growing as mobile devices, IoT, Internet of Things, implementations, and cloud services demand more addresses than IPv4 can provide. Wireless networking operates primarily at physical and data link layers while supporting all upper layer protocols. Physical layer, wireless, uses radio frequency transmission in 2.4 GHz and 5 GHz bands, with 2.4 GHz providing longer range but slower speeds and more interference, while 5 GHz offers faster speeds with shorter range and less congestion. Data link layer wireless implements 802.11 standards, including 802.11n Wi-Fi 4, 802.11ac Wi-Fi 5, and 802.11ax Wi-Fi 6, each offering improved speeds and device capacity. Wireless security evolved from weak WEP encryption through WPA and WPA2 to current WPA3, with enhanced protection against brute force attacks. Access points serve as wireless to wired bridges, converting radio signals to Ethernet frames and managing wireless client associations. For CCNA preparation, understand basic wireless concepts, security protocols, and how wireless integrates with wired networks through access points and wireless controllers for enterprise deployments. Network management operates across multiple OSI layers to monitor, configure, and maintain network infrastructure. SNMP, Simple Network Management Protocol, operates at the application layer, allowing centralized monitoring of the network devices through Management Information Bases, MIBs, containing standardized device information. Syslog provides application layer logging services, with network devices sending log messages to centralized servers using UDP port 514 for real-time monitoring and troubleshooting. NTP, Network Time Protocol, synchronized device clocks across networks, ensuring accurate timestamps for logging, security, and network coordination. TFTP, Trivial File Transfer Protocol, enables simple file transfers for device configuration backups and firmware updates using UDP for minimal overhead. SSH, Secure Shell, provides encrypted remote access for secure device management, replacing insecure Telnet protocol. For the CCNA exam, understand how these protocols work together to provide comprehensive network management, monitoring, and maintenance capabilities essential for enterprise network operations. Quality of service operates across multiple OSI layers to prioritize network traffic and ensure adequate performance for critical applications. Layer 2 QoS uses 802.1p, priority bits in Ethernet frames to mark traffic importance, with values 0 through 7 indicating increasing priority levels for local network prioritization. Layer 3 QoS employs DSCP, Differentiated Services Code Point, marking in IP headers, providing more granular traffic classification and priority handling across routed networks. Traffic shaping controls bandwidth usage by limiting transmission rates for different traffic types, preventing any single application from consuming excessive network resources. Traffic policing monitors bandwidth usage and can drop or remark packages exceeding configured thresholds, enforcing network usage policies. Common QoS implementations prioritize voice traffic for clear phone calls, video conferencing for smooth meetings, and critical business applications over general web browsing. Understanding QoS principles helps design networks supporting diverse application requirements while maintaining consistent performance levels. Network address translation operates primarily at the network layer, Layer 3, to enable private networks to access public internet resources using limited public IP addresses. Static NAT provides one-to-one mapping between private and public addresses, useful for servers requiring consistent external addresses. Dynamic NAT uses pools of public addresses assigned temporarily to private hosts, providing better address utilization. Port address translation, PAT, or NAT overload, maps multiple private addresses to single public addresses using different port numbers, maximizing public address efficiency and enabling home and small office internet access. NAT benefits include IP address conservation by reusing private addresses, enhanced security by hiding internal network structure, and simplified network design with standard private addressing schemes. NAT limitations encompass application compatibility issues with embedded IP addresses, complexity with peer-to-peer applications, and potential performance impacts from address translation processing. For CCNA preparation, understand NAT configuration commands and troubleshooting techniques for common connectivity issues. Effective network troubleshooting follows a systematic methodology ensuring consistent and efficient problem resolution. Step 1 involves identifying the problem by gathering information from users, observing symptoms, and determining the scope of issues affecting single users, departments, or entire networks. Step 2 establishes a theory of probable cause by considering recent changes, known issues, and logical problem sources based on symptoms and OSI layer analysis. Step 3 tests the theory to determine the actual cause, either confirming suspicions or ruling out possibilities to narrow the investigation. Step 4 establishes a plan of action to resolve the problem, considering impact on users, required resources, and potential side effects of proposed solutions. Step 5 implements the solution carefully, documenting steps taken and monitoring results to ensure problems are fully resolved. Step 6 verifies full system functionality and implements preventative measures to avoid reoccurrence. Step 7 documents findings and actions taken, creating knowledge-based entries for future reference and team learning. Now that you understand the OSI layers, let's apply this knowledge to real-world problems. Network issues rarely announce which layer they're affecting, so we need a systematic approach. Physical layer problems are usually obvious. Complete connectivity loss, no link lights, or intermittent connections that improve when you wiggle cables. Think power outages, damaged cables, or equipment failures. Data link layer issues are trickier. You might see high error rates, devices that can't communicate on the same subnet, or broadcast storms that slow everything down. These often point to switch problems, VLAN misconfigurations, or duplex mismatches. Network layer problems prevent reaching other networks. Users can ping devices locally, but can't access websites or remote servers. Check your IP configurations, routing tables, and gateway settings. Transport and application layer issues are more specific. Maybe web browsing fails, but email works, or certain ports are blocked by firewalls. The key is methodical testing. Start with, can we ping the local gateway? Then, can we ping a remote IP address? Then, can we ping a host name? Each step isolates the problem to specific layers. Let's walk through a real scenario. Users report they can't access websites, but internal file sharing works just fine. First, check physical and data link layers. Are link lights on? Can we ping the local gateway? If yes, those layers are working. Next, test network layer. Can we ping 8.8.8.8, Google's DNS? If this works, routing is functional. If we can ping IP addresses but not host names like google.com, that's a DNS issue, application layer problem. If we can't ping external IPs but internal ping works, check the default gateway configuration or routing tables. This layered approach quickly isolates problems instead of randomly trying fixes. Document your testing steps. It helps identify patterns and prevent repeating the same tests. Subnetting appears throughout the CCNA exam, so let's make this crystal clear. Subnetting is borrowing host bits to create more networks. Here's the essential formula. If you borrow n bits, you get 2 to n subnets, each with 2 to remaining host bits minus 2 usable addresses. Here's an example. You have 192.168.1.0/24 and need 4 subnets. You need to borrow 2 bits. 2 to the power of 2 equals 4 subnets. Your new mask becomes /26. The subnet masks break down like this: 192.168.1.0/26 with usable hosts from .1 through .62. 192.168.1.64/26 with hosts .65 through .1 and 26. Then .128/26 with hosts .129 through .190. And finally, .192/26 with hosts .193 through .254. Here's a quick tip. The block size is 256 minus the subnet mask value. For a /26, mask 255.255.255.192, the block size is 256 minus 192 equals 64. You count up by 64s. 0, 64, 128, 192. Practice this until it's automatic. The exam will test your speed as much as your accuracy. IPv6 isn't just bigger addresses. It fundamentally changes how networks operate. With 128-bit addresses, we have enough addresses for every single grain of sand on Earth, several times over. Key differences from IPv4. No broadcast. Everything uses multicast. Built-in IPsec security. Simplified headers for faster processing. Automatic address configuration, SLAAC. IPv6 addresses use hexadecimal. Take a look. Here are some compression rules that you can use to shorten your IPv6 addresses. Remove leading zeros. 0db8 becomes db8. Replace consecutive zero groups with 2 colons, but only once per address can this be used. So our address becomes 2001:db8 FE80:1. Every device automatically gets assigned a link local address, FE80::/10, for local communication, plus potentially a global unicast address for internet access. The /64 prefix length is standard for end networks, giving you 64 bits for host addresses. That's more hosts than all IPv4 addresses combined. Behind every smooth network experience are services working invisibly. Let's examine the critical ones. DHCP automates IP configuration using a 4-step process: discover, offer, request, acknowledge. Your device broadcasts, "I need an IP." Server responds with offers. You'll request one, and the server acknowledges. This happens in seconds. DNS translates host names to IP addresses through a hierarchical system. When you visit google.com, your computer asks your DNS server, which might ask root servers, then .com servers, then Google's authoritative servers. This distributed system handles billions of queries daily. NAT, or Network Address Translation, allows private networks to share public IP addresses. Your home router translates internal addresses 192.168.x.x to your ISP service provider's address, tracking connections by port numbers. This conserves IPv4 addresses and provides basic security. These services rarely fail completely, but when they do, networks become unusable despite perfect connectivity. Wireless adds complexity to our layered model. At the physical layer, we're using radio frequencies instead of cables. The 2.4 GHz bands offer longer range but faces interference from microwaves, Bluetooth, and other devices. The 5 GHz band provides faster speeds with lesser interference but shorter range. At the data link layer, wireless uses 802.11 standards. You'll see 802.11n, Wi-Fi 4, 802.11ac, Wi-Fi 5, and 802.11ax, Wi-Fi 6. Each generation improves speed, efficiency, and device capacity. Security evolved from weak WEP encryption through WPA and WPA2 to current WPA3. WPA3 provides better protection against password attacks and improves security for open networks. Access point bridge wireless devices to wired networks, converting radio signals to Ethernet frames. In enterprise environments, wireless controllers manage multiple access points, handling client roaming and centralized policy enforcement. For the CCNA, understand basic wireless concepts and how they integrate with wired networks, rather than diving deep into RF engineering. Security isn't a single technology. It's protection at every OSI layer. Physical security means locked server rooms and protected cable runs. Someone with physical access can compromise any network. At the data link layer, switch port security limits which MAC addresses can connect to each port. VLANs segment networks, isolating different types of traffic. Network layer security uses access control lists, ACLs, to filter traffic based on IP addresses, protocols, and ports. Firewalls also operate here, inspecting packets and blocking threats. Transport layer security includes SSL, TLS encryption for web traffic, and application data protection. This is what creates the secure connection when you see HTTPS. Application layer security encompasses user authentication, application-specific protections, and security protocols like SSH for remote access. Defense in depth means implementing security at multiple layers, so if one fails, others provide protection. Just remember, no single security measure is sufficient. Let's trace what happens when you check your email, seeing all OSI layers in action. Your email client, application layer, creates an IMAP request to retrieve messages. This gets handed to the transport layer, which adds TCP headers with port 993 for secure IMAP. The network layer adds IP headers with your mail server's address. Your computer consults its routing table and sends packets to the default gateway. At the data link layer, your computer uses ARP to find your router's MAC address. Then, this creates Ethernet frames. The physical layer converts these to electrical signals on your Ethernet cable. Your router examines the destination IP, consults its routing table, and forwards the packets toward your ISP. This process repeats at each router until packets reach your mail server. The mail server reverses this process, sending your emails back through all 7 layers. Your email client displays the messages, and you never think about the complex infrastructure that made it possible. This is the magic of layered networking, complexity hidden behind simple interfaces. Network performance issues can occur at any layer, and solutions must target the right level. Physical layer optimization means using appropriate cable types: fiber for long distances and high bandwidth, proper cable categories Cat6 versus Cat5e, and eliminating interference sources. Data link layer improvements include upgrading switch hardware, implementing VLANs to reduce broadcast domains, and ensuring proper duplex settings to avoid collisions. Network layer optimization focuses on efficient routing, proper IP addressing schemes, and quality of service to prioritize critical traffic. Voice and video need consistent, low-latency paths. Transport layer optimization includes TCP window sizing for high-bandwidth connections and choosing UDP for real-time applications where speed matters more than perfect delivery. Application layer improvements often provide the biggest impact: caching mechanisms, content delivery networks, and application-specific tuning. Remember, adding bandwidth doesn't always solve performance problems. That 10 GB connection won't help you if your application is poorly designed or your switches are overloaded. You now understand the foundation of all networking: how data moves through layers, how different protocols cooperate, and how to systematically troubleshoot problems. This knowledge prepares you for the remaining CCNA topics. Switching and VLAN builds on data link concepts. Routing protocols extend network layer understanding, and network services combine everything you've just learned. For immediate practice, set up a home lab using Packet Tracer or GNS3. Start simple. Connect 2 PCs through a switch, then add a router and create subnets. Build complexity gradually as your confidence grows. Focus on understanding rather than memorization. When you truly understand why protocols work the way they do, you can troubleshoot problems you've never seen before. The networking field offers excellent career opportunities, strong job security, and the satisfaction of solving complex technical challenges. Every organization needs networking professionals, and the skills transfer across industries. Continue building on this foundation. Stay curious about how things work, and remember that every expert was once a beginner. Your networking journey starts with these fundamentals. Now go build something amazing.